V-Ray comes equipped with a number of extremely powerful global illumination or GI engines that can help us recreate pretty much any natural lighting scenario and a good number of unnatural ones should we have a mind to. If we just come into the 3ds Max user interface, if we come up to the render setup dialog, we can just show you where V-Ray's indirect illumination tools are found. And we just want to come along in our tabs to the indirect illumination tab. And here you can see with the systems turned on, we have access to a whole array of global illumination tools. We have access to a number of different global illumination engines. The feature sets of these tools are robust, they're powerful, they give us the ability to easily switch between physically correct and artistically correct approaches to our lighting setups. They can be tuned to be fast enough for even the most demanding of production schedules, and yet at the same time still output high quality images for us. Ultimately, these systems can remove an awful lot of the guesswork that would otherwise be involved in trying to manually recreate a realistic lighting solution. Really, all we need to do is evaluate the lighting needs of our current project, choose the tools we want or need to use. Of course, we need to run through our lighting setup, and then we can have V-Ray's GI engines assist us in achieving our artistic goals. Now, for the benefit of those somewhat newer to 3D rendering, we are going to start this chapter making the assumption that you may be somewhat unfamiliar with just what global illumination is, and so would benefit from just a quick breakdown of its definition and workings. An understanding of just what global or indirect illumination is can probably best be gained by contrasting it to its lighting opposite, which is local or direct illumination, as we see here. By default, adding CG lights into a 3D scene and rendering without any GI systems enabled will give us only this type of local illumination. This computer graphics illumination is not, of course, how light behaves in the real world. This is why we need GI systems in our renderers. They allow us to simulate the physical reality of light, which of course in the real world spent a lot of time, a lot of energy bouncing around our environments. Even the V-Ray dome light, although it does give 180 degrees of light, is still a direct only light source. Let's have a look at the basic GI process. It goes a little bit like this. As direct light is emitted from a source, such as our light here, it will travel until it strikes the surface of an object in our scene. At this point, a lighting phenomenon known as intersurface reflection occurs. All this phrase really means is that a portion of our light's energy will reflect or bounce and create a global or indirect illumination effect in the scene. Dependent upon the amount of energy coming from our light source, we should actually see that our light is able to bounce from a number of surfaces. With each bounce, it will lose a bit of energy, and with each bounce, it will pick up a little bit of coloration inherited from the diffuse properties of surfaces it has interacted with so far. The end result of all of this bouncing is that our surroundings become lit. And even the dark nooks and crannies of an environment will end up receiving at least some level of lighting, even though they may be far away from direct light sources. This complex process is what really gives us the ability to create lighting scenarios that have a very high degree of accuracy and realism to them. We can even conduct lighting analysis tests that will give architects, engineers the ability to measure just how much illumination a given environment and a given set of light sources will produce. Armed now with that basic explanation of global illumination, we are ready to move on to examining a very specific aspect of V-Ray's GI implementation, and that is its use of primary and secondary bounce engines.